Hi everyone, how are you today? Can you hear me? Can you hear me?
Yes.
Okay, thank you. So as I email you, today is the last tutorial. So firstly, we will finish out the topic today is the external flow, and after that, I will use from 10 to 15 minutes to summarize everything to prepare for the final exam. The main theory, the main topic, okay, for the final exam. Okay. Before coming to our topic today, do you have any question about our topic last week, internal flow? Do you have any question? Any question about internal flow, our topic last week? No? Okay. Okay, thank you. So our topic today, external flow. Okay. External flow, let me see. External flow. External flow. External flow is a lab 2. Okay, and as I remember, you have to submit the lab report on Friday. Okay, so external flow, for example, you have an object like this. Oh, what's problem with the signal? Yeah. Oh, what's problem? Can you see my iPad? The screen? Okay, I think you can see it now. Okay, for example, we have an object. For example, this one is a cylinder similar to the lab 2. Okay, and you have airflow over this one. You have airflow over here. Okay, so this one you have is external flow. Okay, and when you have an object and we have airflow or fluid flow over this object, we have two forces applied to here. Is a drag force, FD, drag force, when we could to drag coefficient CD 1/2 rho V square area. This one is drag force, and the lift force FL to CL 1/2 rho V square area. This one is a drag force. This one is a drag force. And this one is a lift force. And CD is a drag coefficient. CL is a lift coefficient. Rho is the density. V is velocity. And A is area. Area. But what's area here? A area. Yeah, you have A area. A. In this case, we have two kind of area, is a frontal area and a planform area. We have frontal area and planform area. Frontal area will be used in almost objects, but the planform area will be used in thin body, or airfoil. So airfoil. Okay. Planform area will be used in thin body and airfoil. Other object we use frontal area. Okay. So if you remember what we did in what you did in the lab 2, you have in the part 2, you have 5 objects. You have circle, you have square, you have diamond, and raindrop facing forward and upward. So the frontal area will be used for circle, for square, and diamond. And the platform area will be used for raindrop. And what is frontal area and platform area? You have frontal area. If you see from this one, from this view, you have frontal. Or if you see from the top view, you have platform area. Okay, so depends on the object. If you have the object is a thin body or airfoil, you use platform area. If you have circle, square, diamond, or other object, not thin body, okay, you use frontal area. Yeah, for example, I have, for example, this one is the lab 2, part B here. You see, we have 5 objects. 5 objects, for example, for circle, it means you will have a cylinder. Okay, so for this one, we will use frontal area. So A frontal will be equal to D times the length of this one is the length of the cylinder in part A times, oh, sorry. What problem? D times the length is a 0.22s for this one, use frontal area. Similar for the square. For the square, the length is 2.228, and you see from this way. Okay, so you have A frontal is L times 0.228 is a rectangle here. With this one is L, this one is 0.228. Okay, for this one, you have rectangle with D and 0.228. For the diamond, how about the frontal area when you see from the side view? Frontal, A frontal will be equal to, you did this one? I think you will submit this one tomorrow, so maybe you know this one already. How about A frontal? Give me an equation here. Yeah, a rectangle. Yeah, this one is a rectangle. Sure. But equation here, you will have this one, L square root times 0.228. Okay. 0.2 L times square root 2 square root, not L times 0.228. Okay. Because you see from here, you will have this rectangle. This one side is L times 2 square root, and another side is 0.228. Be careful about the diamond. Okay, raindrop facing forward and backward. As I said, for the thin body or airfoil, we see from the top view. Or in this case, we use platform area. Platform area. For the platform area, we will have a rectangle, but this side is A plus B, and another side is 0.228. Okay, 0.228. You have the rectangle when you see from the top view. Okay, so A platform will be equal to A plus B times 0.228. Platform, not frontal. Okay, if you use frontal, this one is D times 0.228. Okay, but not frontal. Platform for thin body or airfoil. Okay, it's similar for backward. You will have a rectangle. With this one is A plus B and 0.22s. So platform equal to A plus B times 0.22s. Okay, 0.228. So you got it? You got it?
Sorry, could you just say the diamond again? It's
for
the
this
diamond.
one. Which one?
The diamond.
Diamond. Okay, the diamond here.
So
You
it's
see
L, yeah.
L times 2 square root, because you see this side is L, this one is L. But
Yeah.
when you see from the side view, you will see this one. This one, the rectangle with one side is L times 2 square root. Okay, this one is one side of the rectangle, and another side is 0.228, not L. L times 2 square root times 0.008, I say 0.228. Got it?
Yeah, thank you.
Yeah. Yeah, this one. Diamond. Okay. This one is the lab 2. Okay, so here you use frontal for almost the object, but the platform will be used for thin body and airfoil. Okay, airfoil. About the area, same for drag and lift. And CL and CD is a drag coefficient and lift coefficient. Okay, so how to get this one? Actually, the CD and CL depends on the object. This one is a lecture slide. Okay, and in here, yeah, this one is said about this slide said about the thin body. Okay, CD for airfoil and other thin body is based on the platform area. Platform area is when you see from the top view, rather than the frontal area. Okay, you platform, not the frontal area. This one for airfoil, and you can use this one for raindrop. This one for eclipse cylinder. For we have other objects. We have the CD, but this one is for laminar flow, or when the Reynolds number is smaller than 1. Smaller than 1. When you have Reynolds number smaller than 1, you can use this equation. This equation. Okay, for some common objects, sphere, hemisphere, circular disc. Okay, and this one is for when Reynolds number higher than 10 power 4. For square root, for rectangle root. Okay, you see this one is square root. You can use this one. It's similar to the square in the lab 2. Okay, it's 2.2 or 2. Okay, it's rectangle root, circular, eclipse. Okay, triangle, semicircle. You hear 3D, the cube, the sphere, eclipse. We have so many objects here. So with one object we have the different CD here for streamline body, for the parachutes, for the tree, for the person. So this one, it depends on the person, but this one is the average one. Okay, so the fast person or the taller person, the CDA will be higher. Okay, bike and car and building. Actually, CD will depends on the type of car. For example, for the truck or the semi-trailer, this one is very high, approximately it's 1. But for minivans or the car, it's only around 0.3. Okay, so you can find so many information about CD of car is on the internet. Yeah. Here, this one is I can show you the history of the drag coefficient in car. Okay, in 1920, the drag coefficient is very high, approximately 0.8. CD higher, it means the drag force is higher. It means maybe you need more fuel. Okay, so now the drag coefficient only around here is 0.3, 0.4. Okay, but with some it's only from 0.1 to 0.2. In here with a different model, you have the different drag coefficient CD. Okay, it's around, for example, 0.6 for Fiat Batila here, but for Citroen GS 0.3, and in here for Mercedes A-Class 0.22, for BMW IS is 1.27, Bugatti Chiron 0.36. Okay, and how to get this number? Wind tunnel. It's similar to what you did in the lab 2. You see, you put a car in the full size wind tunnel. Okay, and when air flow over this car, you find the force. This one is the drag force. Okay, and from that drag force, you find the drag coefficient of this car, similar to what you did in the lab 2 wind tunnel. Okay, wind tunnel. So wind tunnel, there are so many applications of wind tunnel in the real life. But in the lab 2, experiment 2, we have a small size, the left side of the wind tunnel. Okay, so CD is very important factors in external flow. Okay. One more thing I want to remind you here is drag coefficient. Sorry, drag force for flat plate. This one is important because this one for the flat plate it means you have which one is a flat plate? You have the drag coefficient for flat plate. You have flat plates. It means this one is very thin. So for one more thing, yeah, drag force. You have drag force here. Actually, this one equal to friction drag and pressure drag, FD pressure. Why we have pressure drag? To remember in the lab 2, in the part A, you have 21 pressure, 21 holes around the half of the cylinder, and you know that in the front, this one 0.1, this one is 0.21, for example. You have P1 will be is positive. It means P1 higher than pressure, free stream pressure, and P21 here is negative. It means pressure 0.1 will be higher than pressure 0.21. Okay, when you have the pressure difference between 0.1 and 0.21, you will have a force applied to this cylinder, and this force is pressure drag by the pressure difference between in front and behind the cylinder. Yep, you're right. Yep, it's 0.064 times 2 square root times 0.228. Yep. Friction drag, this one by the, because when you have airflow over this one, you have the resistance between the airflow and the cylinder. So you will have this one, friction and pressure. Pressure by the pressure difference between 0.1 and 0.21, and friction by the resistance. Okay, so for the flat plate, because this one is very thin, so for the flat plate, FD will be equal to FD friction only. You can assume that pressure is the same. Okay, pressure in front and behind is the same. So FD equal to FD friction. And this one will be equal to CD 1/2 rho V square area. But you see, we have the friction in two sides, will be in two sides of the flat plate. Two sides of the flat plate, you have the flat plate like this. Okay, in above and the bottom here, it on two sides of the flat plate. For example, flat plate is A and B. So this area will be 2 times A times B, frontal area, but 2 times because it's two sides. You have two sides of the flat plate and the resistance on two sides of the flat plate. So this one is 2. Okay, 2 times A times B. This one is the frontal area, sorry, planform area. Because this one is thin body, so we use the planform area. Planform area of this one is A times B, but we have two sides of the flat plate, so you have 2 here. Okay, so you will have the equation FD of flat plate will be to CD times 1/2 rho V square times 2 times A times B. This one is for flat plate. Just only for flat plate. Okay. External flow. Do you have any question about external flow? Any question about external flow? No? Okay. So remember, for some object you use frontal, but some you use planform. Okay, planform. And flat plate, important too. Okay, so today we have 3 questions. Maybe we will go quickly because we have to use 10 to 15 minutes to summarize. Okay. Question 1. We have a bicycle rider want to estimate the drag coefficient CD of her rider and bicycle combination. She measures the projected frontal area to be 0.35 meters square and the rolling resistance coefficient to be 0.8 Newton per meter per second. Rolling resistance coefficient. Okay. Yeah, for example, we have the rider cuts down the hill. This one is this one cuts down the hill. Yeah, the rider mass is this one, and the by mass is this one, and the rider cuts down the hill has a constant phi slope and reaches a steady speed 15 meters per second. Okay, you phi CD. For this one, this one is the hill, and this one is phi. And you have here is this one is rider and I'm not good in drawing. Okay, so for example, this one is a rider and a bicycle. Okay, rider and bicycle. And the mass of the rider, mass of rider, this one, weight of rider, and this one, weight of bicycle. Okay, when we have mass, it means we have weight. And we have the rolling resistance to be 0.8 Newton per meter per second. Rolling resistance coefficient. It means when this one moves down, we will have the resistance force between the hill, the road, and the bicycle. And this one will be upward. Resistance, FR. And do you remember equation to find FR? The resistance, rolling resistance. Do you remember equation to find this one? FR. Do you remember equation? If you don't remember equation, have a look at the unit. You can see the unit. Unit is Newton per meter per second. Newton is the unit of the force, and meter per second is the unit of velocity. Okay, it means FR will be equal to FR or resistance force will be equal to rolling resistance coefficient 0.8 times velocity. You will have Newton per meter per second times meter per second will be equal to Newton. Maybe you can have a look in the unit if we can remember. You will remember the equation. Okay. Moreover, when this one's move down, we'll have the drag force FD, the drag force applied to the rider and the bicycle. And FD equation CD 1/2 rho V square frontal area. In this case, we use frontal area because this one is not thin body. Okay. It means, so applied to the rider and bicycle, we have 4 forces: weight of rider, weight of bicycle, resistance force, and the drag force. And this one moves down a steady speed 15 meters per second. Steady speed 15 meters per second. It means the downward force is equal to the upward force. Actually, in this case, we have the force from the ground applied to the rider and bicycle. Force from the ground is this way. Okay. But in this way, we call it X direction. This one is Y direction. We only have a look in X direction. So we can ignore the force in the Y direction. That's why I not mentioned to the force from the ground applied to the rider and the bicycle. Okay. In this case, when we see in the X direction, it's all the moving direction. Okay, because this one move with the steady speed, so upward force will be equal to downward force. Upward force we have is FD plus FR. Downward force will be equal to weight of bicycle and weight of rider times this one and this one. This one is phi, so sin phi. Upward force equal to downward force. You will have this one. Okay. With sin phi. This one is the equation you have here. With the weight here, weight of bicycle, weight equal to mass times gravity. Weight bicycle equal to mass of bicycle times gravity. Or this one equal to 15 times 9.81. Weight of bicycle. Weight of rider, mass of rider times gravity. Or this one is 70 times 9.81. FR is a resistance force. So FR, as I said, equal to 0.8 times velocity, or 0.8 times velocity is 15. Okay, FD is a drag force. Drag force equal to CD 1/2 rho V square A frontal area. Frontal because this one is not thin body. Okay. With the density, how about the density? Which density? Which density here? Is density of the bicycle, density of the rider, or density of which one? Read density here. Density of which one? The drag force is a force from the fruit flow applied to the object. So the density here is the density of the fruit. And fruit in this case is air. Air. So density here is the density of air. Air density. Air density. And air density in this case, it's not mentioned to the temperature, but you can use, for example, this one is at 20 Celsius. So this one will be equal to 1.23 kilogram per meter cube air density, a standard condition. Okay. FD, drag force, is a force. You remember in the lab 2, you have the cylinder and you have airflow over the cylinder. So you have the drag force, and the drag force in that case is a force from the air applied to the cylinder. Okay, so the density here, density of air. V, you have V here is 15. A frontal 0.35 meter square. Okay, so in this equation, in the right hand side, you have everything. You have weight of bicycle, weight of rider. In the left hand side, resistance force you have, Fr you have. Okay, in the FD equation, you have the density, you have velocity, you have a frontal, so you can find CD. CD. Okay, with CD here, you have is around 1.25. This question is the first question about external flow, so I have you. Okay, but for the second one, I will give you time to do something. CD. Do you have any question? Look good. Okay, it's easy, yeah. It's only easy, yeah. Actually, I think the external flow is easier than internal flow. External is easier. Okay, because for external flow, you only have 2 equations: drag force, lift force. Okay, and drag force, lift force depends on CD, CL. CD, CL, you have from the table, from the figure. Okay. In this case, just remember that we have 2 areas, frontal and planform. Planform only used for thin body and floyd. Other one, you frontal. That's it, easy. Okay. First one, okay. The second one, okay. With this one, I will give you, maybe you will try to do it by yourself. First, okay, we have a water tower. It's a spherical sail with a diameter is 8 meters. The sail is supported by a single 30-meter long vertical cylinder of the diameter 2 meters. A wind with a uniform velocity 20 km per hour blow over the whole structure. You find the bending moment on the base of the tower due to the wind and temperature is 20, structure sea level. Okay. In this case, we have a sail on the top. This one is supported by a cylinder. This one is the ground. And the diameter of the sail, this one is 8 meters. This one is ds, okay, diameter of the sail. The cylinder diameter is 2 meters. This one, DC of the cylinder is 2 meters. And 30 meters long. This one is 30 meters. wind. We have wind here, airflow with velocity 20 kilometer per hour. 20 kilometer per hour. Or this one you can convert to SI unit. SI unit is meter per second. Okay, meter per second. So this one will be equal to 20 meter times 1000 divided by second divided by 3600 or equal to something meter per second. SI unit. This one will be around 5.56 meters per second. Okay, I highly recommend you convert everything to SI unit before your calculation. Okay, you have this system. You have a shell on top. It's supported by a cylinder, and we have airflow with the velocity is 5.56 meters per second. You find the bending moment. Find the bending moment on the base of the tower due to the wind. This one. Okay, bending moment on the base. How to find the moment? How to find the moment? Remember equation? Flow static. Flow static. When you have to find force on plane surface and curved surface, okay, we have some question about the moment. Do you remember equation to find the moment? Moment. Do you remember equation? Moment equal to force times the distance. Force times distance. Force times the distance. The distance. It means to find moment, you have to know the force and you have to know the distance. Okay. In this way, we have two objects. We have the shear on the top is spherical shear. When we have airflow, it means we have the drag force FDS. Drag force applied to the shear, and this one applied to the centroid of the spherical shear, FDS. And you have a cylinder. So you have FDC, drag force applied to cylinder. Okay. And this one I call is LS. And this one is LC, the distance from the force to the ground. Okay. So moment will be equal to moment by FDS for drag force applied to the sphere, the shear, and moment FDC to the cylinder. Or this one equal to FDS times LS plus FDC times LC. So this one is equation. This one equation. Moment equal to force times the distance. LS and LC, I think that's easy. You have LC will be equal to half of the cylinder is 15 meter. The length of cylinder is 30. Okay, so this one is 15. LS will be equal to length. LS will be equal to length of the cylinder 30 plus a half of the diameter of the spherical shear 4 or 34. This one is easy. But how to find the drag force applied to the spherical shear and the cylinder, FDS and FDC. Firstly, FDS. I give you 5 minutes to find FDS. The drag force applied to spherical shell, FDS. And the drag force equation here, CD, spherical shell, 1/2 rho V square, frontal area. Okay, you have 5 minutes to find FDS. And if you had a question, you can ask me. 5 minutes to find FDS. FDS. So it means to find FDS, you have to know CDS, drag coefficient applied to spherical shell, the density, air density, and velocity, and frontal area. So which one we have already have here? Velocity we have, yeah, 5.56 meter per second. And velocity, this one we have already 5.56 meter per second. This one we have. How about the frontal area? Frontal area. Sphere. You have a sphere. So frontal area is when you see from the side view here on the left to the right or right to left is the same. So the frontal area in this case will be is a circle. A circle. This one is a circle. With the diameter is 8. So a frontal here put 2 pi times the diameter, s squared over 4. S squared over 4, yeah. Yeah, pi times 16, frontal area. What's the density? And density This one is air density. The air temperature is 20 Celsius. So we have table. Air density, standard condition. Table 8.8 or 8.9. Let's see. Yeah. Probability of air at 1 atmospheric pressure. The temperature is 20. Okay, 20. We have the density is 1.204 kilogram per meter cube. Air density. Is 1.204 kilogram per meter cube. How about CD? Drag coefficient of the sphere. We have, from the question, we have this figure. The drag coefficient as a function of Reynolds number for the smooth spherical cylinder and the smooth sphere. Smooth sphere. Okay, it means for the smooth sphere and smooth cylinder, CD depends on Reynolds number. Okay, so to find CD, you have to find Reynolds number. So Reynolds number. Firstly, you have to find Reynolds number. Equation rho V D over mu. Rho V D over mu. Reynolds number of the airflow over the sphere. Rho V D or D of the ds spherical seal. With the density, got it here, 1.204 kilogram meter cube. Velocity you got here, 5.56 meters per second. The diameter of the sphere you got here, 8 meters. Viscosity is air viscosity at 20 Celsius. You got from the table 20 Celsius. You have dynamic viscosity here is 1.825 times 10 minus 5. 1.825 times 10 minus 5. Okay. (1.825 times 10 minus 5) is Reynolds number. Similar to what you did in the lab 2. Lab 2. Do you remember it? You have to find Reynolds number of the airflow over the cylinder in the part A. Okay. So Reynolds number, this one. So you have this one, Reynolds number of the sphere will be around approximately 3 times 10 power 6 or 2.98 times 10 power 6. Now we come back to here. For the sphere here, it's a smooth sphere. So you have the Reynolds number. This one is 10 power 6. This one 10 power 7. So 3 times 10 power 3 times 10 power 6. It will be maybe around here. This one is very hard to see. This one, the quality of this figure is very poor. So you will have this one, CD. Okay, CD of the sphere. And this one, I can see in the solution is 0.25, but in here I see here is around 0.27. I think this one is a half. 0.3 will be here, so a little bit below 0.3 is going to be 0.27 or 0.20. Actually 0.25 or 0.27 or 0.26, that's okay. The difference is smaller than 10% in fluid mechanics. That's okay. It's accepted. Okay, it's accepted. So in here, CDS equal to 0.25 or 0.26 or 0.27. That's okay. Okay, the difference smaller than 10%. Okay, good. Okay, so 0.25 or 0.24 or 0.23. That's okay. So FCDS, you got it. So you have FDS. FDS, you will have here is around 233 Newton. 233 Newton. Okay. FDS equal to CDS. CDS you have from the figure when you have Reynolds number. Density from the table at 20 Celsius. Velocity 5.56 given in the question. Frontal area is the area of the circle with the diameter is 8. Done. FDS. Okay. So FDS, you got it. Now FDC. FDC. FDC is a drag force applied to the cylinder. With the same equation, CDC, drag coefficient, CDC times 1/2 rho V square area, frontal area, because this one is a cylinder, not thin body. Okay, and this one is similar to the sphere. You have 5 minutes to find FDC. FDC. The drag force applied to the cylinder. Five minutes. Five minutes, and if you have any question, you can ask me any question. This one is similar to the sphere. The density we have got already 1.204 kilogram meter cube. Velocity is similar, 5.56 meter per second. Frontal area, how about frontal area you have? The frontal area. Frontal area of the cylinder, similar to lab 2. Lab 2, you have a cylinder in part A and cylinder in part B. Okay, And how about the frontal area of the cylinder? Yeah, it's rectangle. Yeah, you're right. It's rectangle. You see here, is the eyes here. You see the cylinder. It's a rectangle. Yep. It's rectangle. This one. Which one side is the diameter of the cylinder. Another one is the length of the cylinder, 30 meter. So a frontal 2 times 30 frontal area. Now CD. Give me the result of CD. You still have time to find CD. CDC. Give me a number here. Yeah, based on this one, you see, for the circular cylinder and smooth sphere, CD depends on Reynolds number. So sure that you have to find Reynolds number first. Reynolds number first. Yep, you have to find Reynolds number here. Rho V d of cylinder divided by mu. Which rho is have here? Rho 1.204 kilogram per meter cube. Velocity, same with this one, 5.56. The diameter, you have 2 meter. Viscosity, you got here 1.825 times 10 minus 5. 1.825 times 10 minus 5. So from here you have Reynolds number. Reynolds number of the cylinder is 7.3 times 10 power 5. Yep. 7.3 times 10 power 5. Okay. So now, thank you. You're right. So now you find CD. CD. We have 7.3, this one 10 power 5, 10 power 6. 7.5, 10 power 5, maybe around here. Around here. You draw a vertical line. Okay. After that is horizontal one. It's higher than CD of the sphere. Okay, and this one, the results we have is 0.33. Okay, so that you can use 0.31, 0.30, 0.33, or 0.34. That's okay. Okay, approximately 0.32. Okay, you know how to get it. So from this one, you have CDC is you have 0.30 or 0.31 or 0.32 or 0.33 or 0.34, that's okay. 10%, smaller than 10%. Okay, CDC, doesn't matter. When you have CDC, you have FDC. FDC in this case, you will have a cylinder is 356 Newton. If you have this question in the final exam, for example, I will give you 4 options. 1, 2, 3, and 4. Maybe the first one 200, the second one 345, 450, and 525, for example. Not exactly the same with the result. Okay, but the difference between the result, this one, and the result, yeah, smaller than 10%. Closest, you choose the closest answer. Closest answer. In this case, 345. Closest with the answer, 356. So you choose second one. Okay, not exactly the same, because as I said in the fluid mechanics, the difference smaller than 10% is accepted. Smaller than 5% is good. Okay, not exactly the same. So don't worry about 0.32 or 0.31 or 0.33. Okay. So you see here, now we have this one, FDC. So you have FDC. Oh, what problem? It's frozen. The screen is frozen. Okay, now you can see it. Okay, now you see the moment equation, you have FDS, you have LS, the length from the distance from the fork FDS to the ground, okay, is 34 meters. FDC, the force applied to the cylinder, you got it? And LC is the distance from the force FDAC to the ground. LC is 15 meters. Okay, so from this one, you will have the moment. This moment, what's the problem with the screen? So from this one, you can will have the moment will be here is 13300 Newton meter, the result. Okay. Moment equal to force times the distance from the force to the ground. In this case, the ground. Okay. As the force in this case, the drag force. Drag force from the air applied to the object. And we have 2 objects here, sphere, okay, and cylinder. And the drag force equal to drag coefficient times 1/2 density, air density, and velocity times frontal area. CD, you can find from the figure based on Reynolds number. Okay, you have any question? You have any question? No, okay, oh good, thank you. The last one today. You have a small soil particle, has a diameter 0.02 millimeter, and the density 2000 kilogram meter cube. You find the time taken for the soil particle to sink 2 meters in the water at 20 Celsius. Assume the falling velocity is constant. You have a particle here like this. Particle here. At the beginning, this one at this position 1. Okay, and this one's moved down to position 2, and the distance here is 2 meter with the constant falling velocity. V here, velocity, V constant. So you have to find the time taken for the soil move from state 1 to point 1 to point 2 time. Do you remember equation to find time? The time taken here. Do you remember? Time equal to high school, maybe, yeah, physics, high school. Remember equation to find time. Time will equal to with a constant velocity. With a constant velocity, time will be equal to distance divided by velocity equal to distance divided by velocity. Distance divided by velocity, or this one equal to 2 divided by v. It means to find time. This one, you have to know velocity. You have to know velocity. And how to find velocity here? How to find velocity here? And how many forces apply to this particle? How many forces apply to this one? You think how many forces apply to this one? How many? How many forces apply to this one? How many forces? First one, we have the weight, the particle, weight of the particle. How many forces? Weight, drag, yes. Buoyancy force, do you remember buoyancy force? Buoyancy force we study in fluid static. When we have an object, is water. If this particle is now moving, if this one is now moving, applying to this one, we have two force, is weight and buoyancy. Buoyancy and weight, if this one is not moving, okay. But in this case, this one's moved down, okay. When this one's moved down, we have the drag force from the water applied to the particle. FD. Okay, so it means in this case we have three forces applied to this particle: weight, buoyancy force, and FD is a drag force. We have drag force because this one moving. Okay, if this one's no moving, we have fluid static, and for fluid static we have buoyancy force and weight. Do you remember it? And this one we have falling velocity is constant. Constant. It means upward force FD plus buoyancy force will be equal to downward one with, we will have this one. With. With the weight of the particle, remember it? Remember equation? Where? With the diameter of this one is 0.02 millimeter, or this one is 2 times 10 minus 5 meter. 2 times 10 minus 5 meter. It's very, very small particle. How about the weight? Weight of the particle. Remember equation? Weight equal to weight density time velocity time mass time gravity. Yes, weight equal to mass time gravity, and mass equal to density time volume. So you will have density time volume time gravity is weight. With the gravity you have here is 9.81. The density is given here 2000 kilogram per meter cube. Volume, V here is this case the volume. Volume of the sphere, V of the sphere, to pi d power 3 divided by 6 is volume of the sphere. So where's easy? You got it? Buoyancy force. Do you remember equation to find the buoyancy force? Fluid static. Buoyancy force. You remember it? Buoyancy force equal to the weight. Yeah, the weight of the liquid in the submerged volume. Weight of the liquid in the submerged volume is the equation of the buoyancy force. Liquid in this case is water, and submerged volume is the volume of the particle, because the whole particle under the water surface. So the submerged volume is the volume of the particle. So it means in this case, we can assume and we have another particle and made by liquid. Weight of liquid is the submerged volume, or equal to the weight of the water in the particle volume. You have a water particle, so it's same equation with weight here, to rho of water time volume of the particle time gravity, rho Vz. Okay, you have a particle full of water and you find the weight. So you have this one, 9.81. Volume of particle here, pi times d power 3 divided by 6. Rho water, 1000. Do you remember this one? Buoyancy force. Buoyancy force we study in fluid static. Okay. Submerged volume is volume under the water surface. Remember this one, you have a boat, okay, under the water. So apply to this one, we have weight and buoyancy force, and submerged volume is this one. Submerged volume is the red one. Yeah. Buoyancy force equal to weight of the liquid is the submerged volume. But in this case, the whole particle under the water surface. So the submerged volume is the volume of the particle. Okay. So weight is this one I call is equation 1. Equation 1. So the weight of the particle is equation 2. We got it. Buoyancy force equation 3. We got it. FD. FD. Drag force equation. CD 1/2 rho v square times frontal area. You see the volume velocity here? Velocity in the drag force equation. Okay, so you have to find velocity to find the time. This means you have to find this one. Velocity. Okay. So from equation 1, 2, it means now FD you know. FD you know. 1 and 2 and 3. Okay, you can find FD. And now have a look in this equation. What we have? The density. Density is the density of the fluid. In this case, fluid is water. So density of water 1000. Frontal area, sphere. So frontal area is a circle with the diameter is d. So this one is a frontal is pi d square over 4. Now, you want to find velocity, you have to know CD. How to find CD and velocity in this case? How to find CD and velocity in this case? This one is a sphere. A sphere. How to find CD? Do you remember it? CD of the sphere in question 2. How to find CD? You have to know Reynolds number. To find CD, do you remember it? To find CD, you have to know Reynolds number. Reynolds number is rho V D over mu. And inside the Reynolds number, you have V, velocity. Can't find velocity without CD based on this one equation 4. You see in the equation 4, can't find V without CD. But you can't find CD if you don't know velocity, because you don't know Reynolds number. And when you don't know Reynolds number, you can't use the figure in question 2. So how to do in this case? How to do in this case? How to do in this case? Not sure. Okay, not sure. Actually, for all conditions or situation, we have to use trial and error methods. This one is you can use in all conditions is trial and error methods. Trial and error methods is mean you assume you have CD is one number with, for example, 0.2, for example, a random one. Okay, yeah, assume you have this one. Based on equation 4, you have velocity. Okay, when you have CD, you have velocity. When you have velocity, you can find Reynolds number. When you have Reynolds number, you have CD, and you try again. I call this one is CD1, this one is CD2. Until the difference between CD1 and CD2 smaller than 10%. This one is Tri-Narrows method. You try again until the difference CD1 minus CD2 divided by CD1 times 100 smaller than 10%. That's okay. This one you can use in all conditions. You can use in laminar flow for turbulent flow. You can use this one. Okay, but in this question, just only in this question, you see you have Reynolds number equal to rho VD over mu. And you see the diameter of this particle is very small. Just only 2 times 10 minus 5. 2 times 10 minus 5, very small. So Reynolds number in this case is very small. Reynolds number is very small. So maybe the Reynolds number in this case will be smaller than 1. Maybe. I guess Reynolds number is smaller than 1. Assume, for example, I assume Reynolds number is smaller than 1. Reynolds number smaller than 1, it means you can use this one. As I show you, when the Reynolds number is smaller than 1, we have, Reynolds number is smaller than 1. We have some equation. For example, for sphere, you have equation here. CD equal to 24 divided by Reynolds number. Okay. 24 divided by Reynolds number. You have, so if you assume a Reynolds number smaller than 1, you can use this equation. Okay. So I assume a Reynolds number smaller than 1. So I will have Reynolds number is, CD equal to 24 divided by Reynolds number. I apply this one to the equation 4. Equation 4 here, you will have FD equal to CD, or 24 divided by Reynolds number is rho V D over mu times 1 over 2 times rho times V square times frontal area is pi times D square over 4. So you have this equation. And easy to find velocity now. You can easy to find velocity now. Because you can cancel out velocity on the bottom here, this one here, so you can have velocity. With velocity, you can find velocity is around, here is 2.18 times 10 minus 4 meters per second. Very slow. 2.18 times 10 minus 4. But this velocity, just only when you have Reynolds number smaller than 1. So after you have velocity, you have to check one, check Reynolds number. If Reynolds number is smaller than 1, you correct. The assumption is correct. But if Reynolds number higher than 1, this one is wrong. You try narrow methods. Okay. Check Reynolds number, rho V D over mu. So this one, you have rho is 1000. V here you have is 2.18 times 10 minus 4, very small, very slow. D here is you have is 2 times 10 minus 5. Very small particle. Okay. And the viscosity here you have is 1.002 times minus 3. Is viscosity of water at 15 or 20 Celsius. So you have Reynolds number here is 4.4 times 10 minus 3, smaller than 1. So the assumption is correct. Correct. You assume a Reynolds number smaller than 1. And after that, you check Reynolds number smaller than 1. So it's correct. But if you have Reynolds number higher than 1, you try and error. You have to use try and error method. No way. Yeah. Because as you see here, Reynolds number depends on velocity. Okay. And you can't find velocity without CD. Can't find CD without velocity. Try and error method is the best way. Is this guy. Just on, as I said, just only in this question, you assume a Reynolds number is smaller than 1. You assume a Reynolds number is smaller than 1 because you see the density as the diameter of the particle is very, very small. 2 times 10 minus 5. So maybe Reynolds number wins smaller than 1. Okay, do you have any question? Do you know why we have to use triangle methods and why we can assume a Reynolds number is smaller than 1? Any question? Okay. So now, summarize. Okay. Summarize. I can show you this one. This one is what we summarize as a week 1. Okay. Week 1 here is the contents. So quiz 1 here based on fluid static. Quiz 2, fluid dynamics. Okay, but not include open channel flow. Open channel flow will be not included in the final exam. Okay, because you don't have any tutorials about the open channel flow. So this one not included. So the final exam will be including from week 5 to week 12, not week 6, week 5 to week 12. Okay, including 3 equations, internal flow and external flow. So now we will summarize. Three equations. Firstly, you have 3 equations. With the first one is the mass conservation. For the mass conservation equation, it means this one is mean when you, for example, we have a water tank like this, and if we have mass in, sigma mass in, mass flow rate, and this one is sigma mass out, mass flow rate, and this tank we call is the control volume. So the mass conservation equation will show you that dmCV over dt, or mass change of the control volume will be equal to sigma mass in minus sigma mass out. If in higher than out, the mass of this control volume increase. Okay, similar to when you have water tank, in higher than out, the amount of water inside the water tank will be increased. The level will increase. Okay, out higher than in, decrease. Okay, and if you have steady flow, it means you have mass in equal to sigma mass in equal to sigma mass out. When you have this one, it means you have mass of control volume is constant. In equal to out, so mass of control volume is constant. You have steady flow. Steady flow. Okay, and if the fluid is liquid. From mass flow rate, you can change to volume flow rate. Volume flow rate in equal to volume flow rate out. Why we have this one? Because volume flow rate equal to mass flow rate divided by the density. And the density of the liquid is almost constant. For example, the density of water, you can use 1000 in no condition. Okay, density of the liquid is constant. Okay, so if the fluid is a liquid, you can change from mass flow rate to volume flow rate. But if the fluid is gas, no, you have to use mass flow rate, not volume flow rate constant. Okay, this one is a mass conservation. The second one, energy equation. For energy equation, remember that you will write the energy equation between 2 points, not 2 sections, not between 2 areas. 2 points. You have to choose 1.1 and 0.2. 0.1 and 0.2. So you will and for example, between 0.1 and 0.2, we add more energy here. We have added energy maybe from the pump, if you have a pump or you have a fan. When you have a pump, it means the pump will convert energy, electrical energy to mechanical energy and to energy of the fluid flow. Okay, you add more energy in the fluid flow, similar for fan. In between 1 and 2, you use a part of energy or you have extracted. We use energy if between 1 and 2, we have a turbine. Turbine, we convert from energy of fluid flow to mechanical energy, and after that to electrical energy. Okay, added and extracted. So if you have this one, you will have the full energy equation is energy P1, P1 over rho Z, pressure heat, kinetic, P1 square over 2Z, potential, that's one, energy P1. Okay. And between 1 and 2, because we add more energy, so we have S added here. To energy 0.2, P2 over rho Z, V2 square over 2Z, that's 2. And between 1 and 2, we use a part of energy for the turbine, for example. So we will have S extracted here. And the last one is SL, energy losses or his loss. And S added and extracted is in form of heat. And if you want to convert this one to the power, you will have P added. Or for example, UP pump. If you have a pump, we will equal to rho Z volume flow rate and S. This one equation to convert from heat to the power. Or if you have the efficiency, this one will be divided by the efficiency. Divided by the efficiency. If the efficiency is 100%, ignore it. Okay. Similar, extracted of turbine power equal to rho Z V 8 extracted or 8 of turbine divided by efficiency. When you want to convert from heat to the power, okay, 8 added and 8 extracted. If you have ideal flow, if you have ideal flow, if you have is a question give you ideal flow, it means you can use no energy loss, SL is 0. SL is 0 for ideal flow. or you will have Bernoulli equation. For ideal flow SL0, you will have Bernoulli equation. Okay. For real flow is mean SL not equal to 0. So when you have this one, SL, this one His loss will be equal to major loss, SL major, and SL minor, major loss and minor loss. With SL major is a friction. If friction His loss, what you did in lab 1 equal to F L over D V square over 2Z. Lab 1. Okay. With F here is a friction coefficient or friction factor. Okay, friction factor. So do you remember how to find F? We did so many times. F here. To find F, you have to know the full flow is laminar or turbulent. For both laminar and turbulent, you can use Moody to find F. Same for this one, you can use Moody. It's the first way. But for laminar, you have equation. This one in lecture 9, week 9, I think, week 9. For turbulent, you have Colebrook equation. Colebrook equation. Okay, so you can use Moody diagram or equation to find F. Laminar turbulent. But I still highly recommend you use Moody, easier. Okay, and when you use Moody diagram, F will depends on Reynolds number and epsilon over D. Okay, Reynolds number and epsilon over D depends on relative roughness, epsilon over D, and Reynolds number. This one is what you did in lab 1. Okay, SL major, SL minor to 6 minus KL V square over 2Z. With 6 minus this KL here is a loss coefficient. This one you have in the lecture week 10. In the week 10, we have so many tables, so many figures to find loss coefficient. You have loss coefficient as the van, as the elbow, as a branch, okay, inlet, exit, so many kind of the loss, minor loss. Okay, so depends on the question. What kind of minor loss you can use week 10 slide to find. So it's for real flow, SL not 0. Okay, so this one is the energy equation. The last equation is the momentum equation. Momentum equation. So different with the energy equation. Momentum equation will be right for a control volume. Here, for example, we have a control volume like this. Or for example, we have a pipe like this. We have this one is state 1, this one is state 2, velocity 1, V2, and in here you have pressure 1, pressure 2, and for example, we have this one is X direction, this one is Y direction. For example, we have the force Fx and Fy applied to this control volume here. Okay. So how to write the momentum equation for this one? The momentum equation, so you just sigma f, the force, total force of the control volume will be equal to sigma beta m v, which beta is momentum flux correction factor. This one is, you can use one if it's not mentioned in the question. Okay, beta, which beta here is a momentum flux correction factor. And beta is approximately 1. This one is equation of momentum. Okay. And because at the beginning we have x and y direction, so we have to write the momentum equation in x and y. But at the station 1 and 2, we have pressure. When we have pressure, we will have the pressure force. Pressure force F1 and pressure force F2. Pressure force will be from the outside to the inside of the control volume. With the pressure force will be equal to pressure times area. F2 equal to pressure P2 times area A2. And for example, we have this angle is alpha 1, this angle is alpha 2. Okay, so how to write the momentum equation in x and y direction? So for this one, for in x direction, we will have sigma f in x direction. Sorry, this one is sigma beta mv out minus sigma beta m v in. Out minus in, this one is equation. Out minus in, this one is equation. Okay, so in x direction, you will have sigma out beta m vx out minus sigma beta m vx in. So now fx, how many forces in x direction? Firstly, we have fx, this one, the force fx. Second one, we have f1 and f2 in x direction, f1x and f2x. But f1x, f1 here, so f1x will be from left to right, same direction with x. So f1x will be positive f1x, and f1x will be to f1 cos alpha 1. f2x, you see f2x from right to left, opposite with x direction. So f2x will be negative in this case. You will have minus f2x is f2 cos alpha 2 equal to beta mv out. Out is means state 2. So you have beta m vx out or v2 out or v2x or v2 cos alpha 2. v2 cos alpha 2 is a positive because v2 cos alpha 2 from left to right, same direction with x. Okay, minus in beta m v in x is v1x. Okay, and v1x from left to right, so positive. So you come v1 cos alpha 1. So you will have the equation in x direction. In x direction. Similarly, in direction, sigma y equal to sigma out beta m vy minus sigma in beta m vy in. So fy in y direction. Firstly, we have fy. Okay, fy f1 like this. So f1y will be upward, same direction y. So f1 sin alpha 1 is f1y. f2y will be downward. Okay, so f2y is minus f2 sin alpha 2 equal to out beta m v2ry or v2y. Okay, v2y, you have v2 here, so v2y upward. So this one is positive v2 sin alpha 2 minus in beta m v in y or v1y. v1y here upward v1 sin alpha 1. This one is in y direction. Okay. This one is how to write the momentum equation. So summarize, if you have y and x direction like this, you will have force and velocity. This one will be positive if F and V same direction with x and y, or in this way or this way. This one will be negative if in this way or this way. So it's positive or negative. This one is momentum equation. Momentum equation. Firstly, do you have any question about three equations here? We have three equations: mass conservation, energy, and momentum. Any question? Okay, the equation is fine. So after that, internal flow. Internal flow. Actually, everything you need for internal flow, you study as the three equations already. For example, here, this one in the left one, you have point 1 here, point 2 here. And you want to find the pressure drop or pressure difference between point 1 and point 2. This one is internal flow. And how to get the equation? Is a left node from three equation, or in this case from energy equation. Okay, so internal flow is on three equation. For example, here, remember we all have to find delta P, and to get the equation in the left node, you write the energy equation between point 1 and point 2, P1 over rho Z, V1 square over 2Z. That's one will be equal to P2 over rho Z, V2 square over 2Z. That's 2. And SL is the energy loss. Okay. And between 1 and 2 is the last report, is experiment 1. You don't have fun, no elbow or something like that. So any loss in this case is only fixed loss or SF. Okay. So between 1 and 2, the pi same diameter. D1 equal to D2. So A1 cross-section area 1 equal to cross-section area 2. Moreover, we have volume flow rate at 1 equal to volume flow rate at 2. So from this one, you will have velocity V1 equal to V2. It means water velocity in this pi is constant. So cancel out this one, kinetic energy. 1 and 2, same height. Cancel the potential energy. So from the energy equation between 1 and 2, you will have this, okay? Or you will have P1 minus P2 equal to rho Z SF, or P1 minus P2 is delta P. This one is equation you have in the left note, the left one. Okay, with SF equal to F over D V square over 2Z. That's it. Why you have equation in the left note. Energy equation. Okay, so that's why I said internal flow based on 3 equations. If you understand 3 equations, internal flow is very easy. Okay. External flow. External flow is what we study today. What we study today is when we have 2 forces. When you have the objects is cylinder and airflow over the cylinder. We have 2 forces here. Is FD equal to CD 1 over 2 rho V square area, and lift force CL 1 over 2 rho V square area. Okay. So because we summarize about this one already, so just remind you that A in this case maybe is some case is the platform area, but in other case it maybe is the frontal area. Platform area just only for thin body. Okay, thin body use platform. Other one use frontal area. Okay, and for the flat plate, you have to times 2 because you have 2 sides. Okay, flat plate. You can see the summary at the beginning of this tutorial. Okay, so it's everything. All equation you have to remember. Not too much, but you have to know how to apply the equation. Is a question. Okay. You have any question for me today? Any question? Okay. So if you have any, as I remember, the final exam will be 22 November. So if you have any question from now to 22 November, you can email me. Okay, I will try to answer you as soon as possible. Okay. So yeah, thank you, and good luck. Okay, I hope that you will have the good results in the final exam and in this subject. Okay, so thank you, and please email me if you have any question. Yeah, thank you. Bye bye. Thank you. Bye bye.